Hi guys, in this video we're going to go ahead and start with new content. We only have chapter 7 and chapter 8 left, and we're going to be doing 7.1 differential equations. So you can read the vocabulary words for the section online. We're just going to go ahead and go kind of into the notes as if we were in a real classroom together. So I start with like the first differential equation that you probably have seen that we've done in the classroom, and that's going to be the exponential growth and decay problem. And this is because, it really applies to what you see in all of your natural sciences. So you could come across it in chemistry, in nuclear physics, and it's really simple, right? So the very first differential equation pretty much anyone is exposed to will just say that the rate of change is directly proportional to a constant and some quantity. So maybe the population depends on your starting population times some constant. So you could say that like population growth. Oh, let me choose a pen. You could say that population growth, the change, we want this to be the rate of change, is equal to some constant times your starting population. So this, we don't know it, but this is a differential equation because you have the function y and you have its derivative. So a differential equation is just any function that has a derivative, right? So maybe it could be, this is like saying y prime equals k times y, but you could have a function with the second derivative and the first derivative. You could add in the third derivative. Any equation that links a function with its derivative is a differential equation. The easiest one, right, is just this linear one because k is constant, and you'll see that we write k as our constant in our word problem examples. So you'll want to continue to do that for the AP exam. And so another thing that I want you guys to know is that when we're solving these problems, you're not going to get a solution that's a number. You're going to get a solution that's an equation or a class or a set of equations. You're going to get a whole new set of functions. So just keep that in mind, and we're going to go ahead and get started because I think the examples really help explain this topic. So example 1 is just classifying differential equations. So the first thing that we talk about is the order and the degree of the differential equation. So the order refers to the highest power. Well, I'll say the highest derivative. And the degree is just like with any polynomial function, is the highest power of x. And we're going to start with this first term, right? And so the highest degree of x here is 1, and we can see this is a second order. And I'll change the color. So this, we would say, is a second order differential equation. With a first degree polynomial. So you would just say it's second order first degree. And so that's pretty easy, just classifying the function. Example 2 is now going to have you kind of prove, right, that this function is a solution to the differential equation. And so we're going to start by, we know that y, Murphy, stop that. We know that y equals x to the 4th minus 5x plus 1. And we're going to be solving y double prime minus 12x squared equals 0. So we're going to start by finding y prime, which will be 4x to the 3rd minus 5, and we can write plus 0, but obviously there's nothing there. And then the second derivative, right, is going to be 12x to the 3rd. And so when we plug that in, we see that this turns into 12x to the third minus 12x squared equals 0. So all we did here was prove that this is a solution to the equation. And I want you to note is that because we're putting in the second derivative, that it doesn't matter what this number is or this number is, these constants are irrelevant, right? Like no matter what those numbers are, you will find a solution to this problem. So you could really say that anything, right, of a constant, and you could say plus a constant times x plus a second constant is a solution to this differential equation. And that's why we say you could have a set of functions that would count as your solution. Okay, example B says show that y equals, and here you see they don't give you a number, they just tell you a constant, that y equals x to the fourth plus c1x plus c2, where c1 and c2 are constants, is a solution to the differential equation. And here we see this is the same differential equation to the last problem. So again, you're going to find the derivative. So I have 4x to the third plus c1, and the second derivative, which will give me 12x squared, and that's it. So then I would just, once again, prove that 12x squared minus 12x squared equals 0. So the function y equals g of x is a solution to the differential equation. I think overall it's pretty easy at this step. Differential equations become more difficult when you're trying to find what that function looks like. Okay. Example 2, verifying solutions to differential equation. Oh, we're continuing the last example with this last one. So here it tells you to show, and I'm just going to go ahead and write y. Oops. I'm going to write that y equals x squared minus x to the third y plus 3 y to the fourth, right? And it just equals some constant. And so it's kind of like saying that, because it's going to turn into 0 later, as a solution to this differential equation. So what I'm going to do is take the derivative here, right? So this turns into 2x minus x to the third. And I'm going to take the derivative of y first, so we're using implicit differentiation and the chain rule here, right? So I would say this is dy dx minus, again, now the derivative of x to the third, 3x squared times y, plus 3 times 4 is 12y to the third dy dx, and all of this will now equal 0. And so the second thing you want to do is get your dy dx's together. This is exactly like what we did when we were learning implicit differentiation. So I have minus x to the third dy dx plus 12 y to the third dy dx equals plus 3x squared y minus 2x. And then I'm going to go ahead and take the dy dx out. I can pull this out like this by saying, well, this is 12y to the third minus x to the third, right? And this equals 3x squared y minus 2x. And then I can solve for dy dx by dividing by this term. So that dy dx equals 3x squared y minus 2x divided by 12 y to the third minus x to the third. And so we've therefore proven this statement over here. Alright, now this is really what you're going to be seeing on the AP exam, and that is applying it for this unit, applying it to word problems. So we're going to read through these together, and for your homework you have 6 to do. So example 4 says if the pressure P applied to a gas is increased, so I'm just going to write, well, the pressure P is increased while the gas is held at a constant temperature. So remember how earlier I talked about we write K as our constant. So for constant temperature, I'll just put this, then the volume V of the gas will decrease. So V will get smaller as P goes up. The rate of change of the volume of gas. So rate of change tells you you're going to have the derivative of the volume of gas. And here it's going to be with respect to the pressure. With respect to the pressure is proportional, okay, is proportional to the reciprocal. So when they tell you the reciprocal, they're telling you that it's going to be in the denominator of the fraction of the square of pressure. So pressure will be squared. And again, there's going to be some constant K. So this is going back to the very first type of differential equation we looked at. So then which of the following is a differential equation that could describe the relationship? So really what we know is that dV dP equals K over P squared. The only question now is K positive or is K negative? Right? And because the volume is decreasing, right, the rate of change has to be negative. So because volume is decreasing, the rate of change has to be negative. And so that gives us option C for this answer. dV dP equals K over P squared, where K is a negative constant. Alright, for the next one we see the weight of a population of yeast is given by the differentiable function, where W is measured in grams and T is measured in hours. And we know that, right, W is in relation to T. The weight of the yeast population increases with respect to T at a rate that is directly proportional. Okay, so here, this was their way of telling you that they're inversely proportional. Here, we see that the weight, right, of the yeast population is directly proportional. Oh, so the rate of change is directly proportional to the starting weight. Kind of like how we talked about the population. So here, I would say dW dt is directly proportional to the weight. Okay, and that's going to be times some constant. And so when T equals 10, the weight is 200 grams and is increasing at a rate of 5 grams per hour. So now all you have to do is solve for dW dt. So we say, well, 5 equals 200K, so that K equals 5 divided by 200. Then we would say K equals 1 over 40. So that dW dt equals, we're going to have W times 140. And once again, we're left with option C. And so that's it for today's note. I think this section overall is pretty easy. If you have any questions, you all know how to contact me. So please don't hesitate. Thank you. Bye.